So as you can see in this figure, the slot format configuration can directly impact 4 different parts. First one can be the throughput, second can be latency, and can be coverage, and can be RACH planning as well. So let me first explain this kind of latency, RACH planning, and coverage. Latency part, for example, assume that you are giving a different slot configuration. Okay, for that part, assume this is your slot configuration as you can see here. So you are using 424. So the uplink would be coming at this particular slot. So for example, assuming now you have a downlink transmission. So for every downlink packet, right, being received by the user, you need to acknowledge this packet, right? So you need to send the acknowledgement. So he need to wait until he received the time of switching from downlink to uplink to transmit the uplink acknowledgement here. So this is the delay which being so this can be impacting your RTT. So in this case, for example, you have 8 to 2. So you have to wait, instead of waiting, for example, 3 slots, now you have to wait. If you transmit downlink here, journal B, you have to wait until they here to transmit it. If you're using, for example, this kind of configuration, which is 3 to 1, which is 2 downlink and 1 flexible uplink, you can see that now it's even more quick feedback will become in the uplink. And as a summary for that, different slot format in general allocation can influence the downlink HARQ feedback, which is being sent in the uplink data, and also the scan and uplink data scheduling in general. Uplink data also can be more quick being sent whenever you having a slot format coming in the beginning. This is also can reduce the RTT delay in general. The second part, it can also improve the shorter SRS transmission period, right? Because SRS usually is coming in the flexible or coming in the uplink. So in this case, you can have a more shorter or more quicker SRS, as for example this particular case here, and this can improve the performance of the MIMO or the Massive MIMO performance in general, because SRS sounding reference signal, whenever it's coming more, having more reliability, this can improve the performance as well. The second part, that's about the RACH planning here. Actually, have two different combination or planning for RACH, right? Which can be long or short planning. The long preambles or short preambles, long preambles require minimum 2 continuous slots, which is having 1 millisecond. It requires 1 millisecond, which means it requires minimum 2 slots. So if you use, for example, this particular configuration here, this means you cannot use it, or this configuration. For example, assume now you have this one DDDSU, and this is repeated every time. So in this case, you have only 1 slot for uplink. So this case would be open 5 millisecond only. So this case, long preamble will not be supported. So you need to take care whenever you are doing the planning for slot or RACH planning as well. And the same here, if you're having 2 for uplink, this means the long preamble now is being supported. And long preamble is very useful whenever you have a macro site, and especially for macro sites, because it's having a larger root sequence index. So this can give you a much better RACH performance. This kind of short preamble can be more beneficial whenever you speak about the milliwave. It will be for that. Can be done because you have milliwave. Particularly, it might be used only for small cells and require less cell radius, while the long format having higher cell radius. The third part is about the coverage. As you can see in the coverage here, I'm giving 3 different slot format and the configuration, a slot assignment configuration. As you can see here, the first part, I'm assuming you have 8 to 2. So we're having 7 slots for downlink, then 1 for mixed between uplink and downlink. So as you know, the SSP is using 4 symbols, right? And usually transmitted, supporting up to 8 SSP, right? Being transmitted in for the SSP beam swapping. So this usually transmitted in the first 5 millisecond or the first 4 slots here. It can be repeated again, but in the first 4 slots, as you can see, and every slot will having 2. So as long as you have enough slots here, you can transmit and get up to the maximum SSP. This is in case of your network supporting this SSP, 8 SSP. And the second case here, for example, assume you're having DDSU. So you can see here, you have 2 slots for, you have 3 slots for downlink. Then number 4 will be mixed between downlink and uplink. So this also depends. You can have even up to 6 or 7, depend on how many symbols here is being used for downlink, because downlink needs the SSP needs at least 4 symbols, right? So this is the symbol number 8 will not be used because this one is partially used by downlink with slot number 3. So you have only maximum up to 7, and sometimes it can be even 6 if you're having a list symbol within this special slot. This is one case. The last case here, and whenever you have a less SSPs transmitting, this can impact your coverage, SSP coverage especially, because you'll have, instead of narrow beams, you'll have more wider beams. So this can impact even the quality or the coverage. The last part here, it's as you can see, it's using DDSU, so it's 2 downlink and 1 special. So this can use up to 5 SSP, and even sometimes can be 4. So this is also having less performance. Now, how this can impact the performance for the downlink or uplink throughput? As you know, there is allocation ratio, right? We can give a ratio between downlink and uplink. So assume, for example, for this pattern, it's using DDSU and it will be repeated. For example, this 2 milliseconds will be repeated 5 times. So this is, for example, the ratio which you have it. If you calculate the number of total downlink symbols, I will show you now quickly how I calculated this. Downlink symbol is 280. So, and this is the downlink of the main symbols used for downlink, for example. How many? 105. This is equivalent to ratio of 70, and you will have 25 for percent for uplink. So 70% of the resources or symbols within the frame, it will be used for downlink, and 25% for uplink, and the remaining will be overhead or SRS. And for example, for this particular case, second one, it's having higher ratio in downlink, means that this one can give much higher speed in terms of downlink, and this one have a much lower speed in terms of uplink and very high speed in terms of uplink. So as you know that this is a factor of throughput, let me quickly take you through the calculation about that part, how I made the calculation and how it can impact the throughput. I will show you, like, if you change this value, how it can impact the throughput. So as you can see here in this table in the middle, this is one which I was showing in the slides. As you can see for this table, I have a different patterns here, for example, the DDSU. So here how I calculated the 280. This is 280 is simply, if you are using SCS 32 kHz, it will be equal to the 20 slots. You usually have 20 slots multiplied by the 14 samples. This is the total number of samples which you have here. The downlink of the MA symbols, for example, this is the formula which is being used. For example, this will be equal to the number of samples per slot. For example, how many samples you have in per slot, multiply. So the number of samples is fixed to 14, right? So the first part here, it will be 14. Let's put this one here. So the first one will be 14 as showing in the top left here. The second part here as showing is asking you for the number of downlink slots. As you can see here, how many downlink slots you have? You have 2, right? 2 downlink slots. So this one will be multiplied by 2. Then it will be multiplied by repetition within 10 milliseconds. So the repetition will be, you have 2, and this is like 2 milliseconds, so it will be repeated 5 times. So we need to multiply again by 5. Then it will be plus the special slot here. How many special slots you have? For example, this is plus the flexible slots. Consider this is for uplink. This is if you are speaking about downlink. This would be plus number of downlink samples within the flexible slots, which is how many samples you have. You have 11 for this particular configuration, so you multiply by 11. And how many number of slots you have in general for S? You have only one S, so it will be multiplied by 1. And this will be repeated again for 5 times. So this will be the configuration, and you apply the same here and there. And for the throughput, for example, assume now I'm using this kind of DDSU, which is the first one. If you look into this speed now, it's like saying as 1.2, for example. If I change it to, let's start first with this first one here. DDSU, this is showing as 70%. So this is changing this kind of value down here for this one, DDSU. So if I change it this one, and now it's giving, because you have the overhead or the downlink shows 70%. So now it's changing, for example, for this particular configuration, which is DDDSU 1131, this one. So now I'll change this one to be DDSU. So you see now the throughput increase because you have 6% higher in downlink. However, the uplink will be impacted compared to the previous one. And actually, this is the end of today's session. I hope if you like the session to press like and to comment, and I will upload this kind of Excel sheet in the video description. You can go through it and download it and enjoy it, and please share it with your friends, and stay tuned for the next sessions about the remaining for the 5G planning and non-standalone. Thank you, and see you next session.